Hi everyone, welcome back to Calc 3. I'm Dr. Matthew Michael here at NJIT. So last time we left off talking about vectors, vector addition, scalar multiplication, and I said that we that we aren't using multiplication yet. It's because there's going to be two types of vector multiplication, the scalar and the vector multiplication. When you multiply vectors together, you either get an output that is a scalar or is another vector entirely. The first one's the dot product, and the next one is the cross product. So let's take a look. So the dot product is useful comparing between vectors. We'd like to know the difference between the angles of them. And so the dot product arises from that look to the difference between vectors. Thankfully, we can use the law of cosines to do this. Similar picture from before, we're crossing the difference between them. And the difference between these is the opposite side, w squared. The magnitude of w squared is equal to the magnitude of u squared plus the magnitude of v squared minus 2uv cosine theta. That's just the law of cosines. Using the definition of the magnitude, plug it in, and we're going to get and move the negatives to the other sides so they cancel out. Everything except for 2uv cosine theta on the left in your reference frame, and 2 times u1v1 plus u2v2 plus u3v3. That's an odd, weird thing right there. And so divide by the magnitudes u and v, and you get the angle theta is arc cosine u1v1 plus u2v2 plus u3v3 over the magnitude u and v separately. That numerator is incredibly important. It transforms a vector understanding into a scalar concept. What do I mean by that? That means that I can take this vector u and v and I can actually compare things, and it's hard to really say, okay, so it has some strength in the x direction and some strength in the y direction, and when they start going in these weird shapes, we need a way to turn all that weirdness into a single, easy to calculate number. What's that number but a scalar? How far off is it? And we can compare it to stuff. So that numerator, that u1v1 plus u2v2 plus u3v3, is what we call the dot product, or scalar product, because it is that scalar. So if it's three-dimensional, it'll have 3 terms to add. Two-dimensional, 2 terms. 100-dimensional, well, guess what? You're going to have 100 terms to add up. So we can also write the angle between as the arc cosine, or inverse cosine, the dot product of u and v over the magnitudes of u and v. An interesting case pops up, though, when we have perpendicular. So if theta is equal to pi over 2, or 90 degrees if you prefer, well, apply cosine to both sides, you get cosine of theta is equal to 0, or arc theta is equal to arc cosine of 0. So what's that mean? That means that for perpendicular numbers, perpendicular vectors, the dot product is going to be 0. We'll come back in a second to that. Let's find an angle measurement between vectors, shall we? So two-dimensional vectors, 2 and negative 2, and v being 5, 8. Find the dot product. We get negative 6. Find the magnitudes, 2 square root of 2 and square root of 89. Well, we know the formula, right? Theta is equal to arc cosine of the dot product over the magnitudes. So arc cosine negative 6 over 2 times the square root of 2 over 289. 2 and a negative 6 cancel out to be negative 3 over square root of 178, and take the inverse cosine of that lovely ball of goo. That's going to be 1.798 rad. So it's less than pi. It's also going to be more than pi over 2, which makes sense because the dot product was negative, which means that they're more than 90 degrees apart. Three-dimensional time. U is 3, negative 1, and 2. V is negative 4, 0, and 2. Find the dot product. Negative 8. Find the magnitudes. Square root of 14 and 2 square root of 85. Plug that into the formula. We get 2.069 radians. Remember earlier when I said that the perpendicular have dot products that are 0? We will have multiple terms for this. Orthogonality. The vectors are perpendicular, they're orthogonal, they're normal, and depending on who you talk to, they'll use different terms relatively interchangeably. They have slightly different connotations. I will use them in those different connotations because of that. I like orthogonal better when I'm talking about vectors. I like normal when I'm talking about planes and vectors. I also like using the term normal when it comes to unit length. So, I will use all three, perpendicular, normal, and orthogonal, but I like orthogonal best. So, plug it in, dot product time, calculate it out. These two vectors, while they don't look like they're orthogonal, really are. Because when you multiply the 3 times the 1, the negative 1 and the negative 1, and the 2 and the negative 2, they all cancel out. So, what are the properties of this dot product? Thankfully, it is commutable. If you flip the order, it doesn't change anything. Constants can move around at will. You can distribute the dot product just like multiplication. Interestingly enough, take a look at number 4. U dot U is equal to the magnitude squared. What? Right? We'll take a look earlier when I did the definition of the dot product. If I replace V with another U, that becomes U1 times U1, U1 squared, plus U2 times U2, U2 squared, plus U3 U3. So that's U1 squared plus U2 squared plus U3 squared. That is the square of the magnitude. So that's what it means by that. And also, 0 times, if 0 is a vector or 0 is a scalar, it's still going to be 0. And so it's very useful in kinematics to break it down into the horizontal vertical components of vectors. And we've done this before in physics when we're talking about the motion of a ball or a rock going off. We'd find out, okay, the y component's affected by gravity, but the x coordinate isn't, so the equations of motion would differ for the two components. Breaking those up into its component parts, we tend to say that the horizontal velocity is the velocity projected onto the horizontal vector, I, for example, and the vertical velocity is the velocity projected onto the vector j. However, in Calc 3, because remember we're seeing how vectors affect space, time, and geometry and calculus, we're going to be more interested in how the vectors interplay on itself. Because I have these two vectors here, I want to see how much of this vector, is in this direction. Neither one of this is in a purely horizontal or vertical motion. But using dot products, I can do this. So take a look. So I have a vector u. I want to project it into the v direction. In this case, v is horizontal, but sometimes it might not be. And so depending on the case, it could be in the positive u direction or v direction, or it could be in the negative v direction. So notice the lengths differ, different shapes. different angles. Notice though that it is the horizontal aspect of this, so it will be the cosine aspect of that. Notice the v is projection of u in the v direction. That's why v is on the bottom, u's on top, and that's really confusing. So projection of u into v, that's why v is down below, is in the direction of v. But I want you to remember from earlier, cosine was, if you remember, theta, if you remember, was arc cosine, the dot product over the magnitude, which would mean cosine of theta is equal to the dot product over the magnitude. So plug it in. So if the projection of u in the v direction is magnitude of u cosine theta, that's also the magnitude of u, the dot product over the magnitudes. Well, the magnitudes of u cancel out. And this is really just saying, well, dot product u and v, and then divide by the magnitude of v. So basically you're taking out the length of v, and you're only paying attention to how much is in that direction. So remember, dot products in their aspects, we're trying to compare these vectors u and v. So by multiplying them, I'm comparing how much do they overlap. So let's find some projections, shall we? Let u be 3i minus 5j plus 2k, and v be 7i plus j minus 2k. Well, using an alternate way and using some weird finagling, this works. Just if you remember that v dot v is just the magnitude of v squared. So if I multiply by v, and if I'm careful, I do get this formula to come out. So this is another formula for the projection, as long as you're careful. So u dot v over v dot v, so that's 3 times 7, negative 5 times 1, 2 times negative 2, that's going to be 21 minus 5 minus 4. V dot v, that's just going to be the magnitude squared, so that's 49 plus 1 plus 4. I wrote the wrong number down. That's 49 plus 1 plus 4. So that's going to be 12 up on top, 54 on bottom, multiplied in the direction of our vector, scalar multiplication, 14 over 9i plus 2 ninths j minus 4 ninths k. So that's how much of the vector is in the j direction. Anything else, we could actually subtract that from u to find out what's not in the direction of v. What part of the vector is perpendicular or orthogonal to v. It's a lot you can do with dot products. Multiplication gets crazy. Hope this was helpful. Have a great day.